You know that feeling, that sinking feeling you get when you're studying for some kind of technical certification?
Oh, I know it well.
You're doing fine, you think you've got the concepts down, and then you flip the page to the architecture section.
The dreaded architecture diagram.
Exactly. And suddenly you're not looking at a network map anymore. You're staring at what looks like alphabet soup that someone just spilled on the floor.
Yeah, an explosion of boxes and acronyms.
But
AMF, SMF, UPF.
lines going everywhere, dotted lines, solid lines. It's a total mess.
It's the wall of complexity. And
Mhm.
honestly, that's never more true than with the 3GPP standards.
Right, the global specs for mobile networks.
And they're notorious for packing just a world of engineering into one tiny diagram.
Well, today we're going to face that wall. We've
Mhm.
pulled one very specific, very notorious diagram from the standards. I think technically it's figure 4.2.41.
Doesn't exactly roll off the tongue.
No, but what it shows is the blueprint for 5G roaming with local breakout.
And it sounds dry, but that diagram, it's really the secret sauce. It's the reason your phone just works when you step off a plane in another country.
It's a map of how everything connects.
It really is a map of international cooperation, actually.
So our mission for this deep dive is to decode it. We're going to strip away the jargon, break this thing down into, let's say, 3 simple layers.
Okay.
The path your data takes, the brain that controls it, and the security that holds it all together.
I like that approach, turning the static image into a story.
So to start, let's just get the geography right. If you're looking at this diagram, how do you even orient yourself? It's split right down the middle.
Right. Okay, so think of the diagram as a map. Just draw a vertical line down the center. Everything on the left side is the visited network.
The VPLMN.
VPLMN,
Okay.
exactly. Visited public land mobile network. It's where you physically are.
Mhm.
So say you're a tourist in Japan.
The left side is where my feet are planted, my reality.
Correct. So then the right side is the home network, the HPLMN. That's your service provider back home, say, in the U.S. It's where your contract lives
And where the bill comes from,
and where the bill comes from.
crucially.
Okay, that's simple enough. Left is Japan, right is home. What about the horizontal layers? There's clear top and bottom.
This is maybe the most important distinction in modern telecom. The bottom layer. That's the doing layer.
The user plane.
Exactly. It's the physical path your data takes when you watch a YouTube video.
And the top must be the thinking layer.
The thinking layer. That's the control plane. It's where the network decides, if you're allowed to watch that video, what quality you get, what rules apply.
Thinking versus doing. I like that. Let's start with the doing part, the bottom layer. It feels more tangible.
It is. So this is the data path. In the diagram, it's that little train track along the bottom. UE to RAN to UPF to DN.
Let's walk that track. First stop UE
User equipment. It's just engineer speak for your phone.
or tablet or whatever.
Right, anything connecting. Okay, next stop on the track. RAN.
Radio access network. That's the cell tower. The thing you see on the side of a building that's catching the radio waves from your phone.
Got it. Now this is where it gets interesting. The line goes from the power to a box called UPF.
The user plane function. This is maybe the most important box in the 5G data path. Think of it as the main gateway, the router.
The exit door.
The exit door is a perfect way to put it. It's where your data leaves the mobile network and gets onto the real internet.
And that leads to the final box, the DN.
Data network,
Yeah.
Netflix, Google, whatever you're trying to reach.
So, phone to tower to gateway to the internet. Seems straightforward, but the diagram's title is Local Breakout. Why is that so important?
This is the game changer. Let's go back to our traveler in Japan with an American SIM card.
Yeah.
In the old days, with what we called home routing, your data would take this massive, insane detour.
Okay, walk me through the detour.
So you click on a link for a local restaurant map in Tokyo. Your phone sends the request to the Tokyo Tower. Then that request would get tunneled all the way back across the Pacific to a gateway in the US, exit to the internet there, find the Tokyo map, and then travel all the way back across the ocean to your phone.
That's absurd. You're crossing the Pacific twice for a map of a place 5 miles away from you.
It's incredibly inefficient. It creates high latency, that lag you feel. And for the operators, it's expensive. You're eating up all this international bandwidth.
So, local breakout is the fix.
It's the fix. Look at the diagram. Where is that UPF box located?
It's on the left side, it's in the visited network in Japan.
Exactly. That is the entire point. The network says, hey, this user is just surfing the web. We don't need to send this all the way back to the US. Let's break it out to the internet right here in Tokyo.
So my data path is just phone-Tokyo Tower, Tokyo Gateway-Tokyo Internet.
Precisely. Your identity is managed from home, but your data takes the shortest path. That's why 5G roaming feels so fast.
That makes perfect sense. I mean, physics wins. But if the data path is that simple, why is the top half of this diagram so unbelievably crowded?
Because speed is easy.
Permission is hard.
Permission is very hard.
So this is the control plane.
Right. And in 5G, this looks totally different from 4G. You see that long blue horizontal line connecting all the top boxes?
Yeah, it looks like a bus line or something.
That's what it is. It's the service-based architecture, or SBA. In older networks, every box had like a dedicated wire to every other box it needed to talk to. It was spaghetti.
That's a total mess to manage.
A nightmare. In 5G, every function just plugs into this service bus. They're not hardwired, they just talk to each other.
How are they talking?
They're using APIs. It's just like modern software development. These boxes, we call them network functions. They're basically microservices.
You're kidding. So they're speaking HTTP.
HTTP2 with JSON payloads. It's a fundamental shift. The telecom core isn't a bunch of custom hardware anymore. It's software.
It's a cloud application.
It really is. So let's meet some of the key players on this bus. We're still on the left side, in Japan. The first box your phone talks to is the AMF.
They access a mobility management function. The doorman.
The doorman or the concierge. Yeah. When your phone turns on, the AMF is the first one it greets. It handles registration, and it tracks you as you move between towers.
Okay, so AMF is the welcome wagon. Who's next?
The SMF, the session management function.
They really weren't creative at the names, were they?
Engineers are not poets, no. The SMF is the traffic controller. Remember our UPF gateway? It's strong, but it's dumb.
It just moves packets.
It just moves packets. The SMF is the brain that tells the UPF, hey, open a data tunnel for this user and route their traffic out to the internet.
So AMF manages the user, SMF manages the session.
Perfect. Then you've got the NSSF.
Network slice selection function. Okay, slicing is one of those huge 5G buzzwords. What's it doing here?
Slicing is basically creating a dedicated virtual lane on the network highway. Maybe you need a super low latency slice for something critical, or just a high bandwidth slice for streaming.
And the NSSF picks my lane for me.
Yes, but here's the roaming challenge. The network in Japan doesn't know what a gold tier plan from the US means. The NSSF's job is to translate. It maps your home service level to an equivalent slice that's available locally.
That sounds complicated.
It can be. And guiding all of this is the PCF, the policy control function.
The rule book.
Exactly. The rule book. It's constantly checking, is this user allowed local breakout? Do they have a data cap? Should they be throttled?
Okay, so we have a doorman, a traffic controller, a translator, and a rule book, all in the local network. But there's a huge problem.
What's that?
I'm in Japan. They don't know who I am. The AMF in Japan doesn't have my password or my subscription details.
You're absolutely right. It looks at your SIM, sees you're from the US, and says, I have no idea who this is. It has to phone home.
So now we cross the border to the right side, the home network.
We have to get to the source of truth.
And who are the big players back home?
Two really big ones. First, the UDM, Unified Data Management.
The master database.
The ultimate database. It has your encryption keys, your profile, what slices you're allowed, everything. If you're not in the UDM, you don't exist.
And the second one?
The AUSF, Authentication Server Function.
The security guard.
The security guard, exactly. When you try to connect in Japan, the AUSF back home runs this cryptographic handshake to prove you are who you say you are.
So the left side has the gear, but the right side has the keys to the kingdom.
Correct. And they have to talk to each other securely.
Which brings us to that bridge in the middle of the diagram. There are two boxes sitting right on the border, labeled SEPP.
VSEPP on the visited side, HSEPP on the home side. This is where 5G gets really serious about security between operators.
SEPP, what's that stand for?
Security Edge Protection Proxy.
It sounds intense. What is it actually doing?
Well, you have to understand the problem it solves. In, say, 4G, when operators connected to each other, it was sometimes a bit too trusting.
A walled garden, where if you were inside, you were trusted.
Pretty much. And that could be exploited. In 5G, we moved to a zero-trust model. The operator in the US does not want the operator in Japan to see the internal map of its network.
It's topology.
Right. They don't want them to know the private IP address of their UDM, for instance. That's sensitive data. If a hacker knows your topology, they know where to aim their attacks.
So the SCP acts like a mask.
It acts like an API gateway and a firewall rolled into one. Think of it like a diplomatic courier.
Explain that.
Okay, so the AMF in Japan wants to ask your UDM a question. It can't send the message directly. It's not allowed to. It hands the message to its local VSEPP.
The visited SEPT.
Right, and the VSEPP encrypts it, it filters it, and it hides the internal address of the sender. That's called topology hiding.
And then it sends it across.
It sends it across that special interface, the N32, to the HSEPP on the home side.
So that N32 is the only pipe connecting these two massive companies.
The only one.
Yeah.
It's heavily encrypted. The HSEPP then receives the package, decrypts it, validates it from a trusted partner, and only then passes it to the internal UDM.
It's like an airlock on a spaceship. The two networks never actually touch. They just pass secure messages through this tiny window.
That is a perfect analogy. It completely prevents attackers from mapping out your internal network from the outside.
Yeah.
All they can ever see is the edge.
Wow. So, stepping back, this diagram, it's not just a tech spec, it's a treaty. It defines how two competing companies can cooperate without having to fully trust each other.
It's a dance of trust but verify, absolutely.
Okay, I want to see this dance. We've defined all the players. Let's do the full story, start to finish.
Let's do it.
Scene. I land at Heathrow. My phone's been in airplane mode. I switch it off. What's the very first thing that happens?
Step 1, registration request. Your phone, the UE, finds a local tower, the RAN, and sends a "Hello, I'm here" message
The tower gets it and passes it on.
to the local AMF, the doorman.
And the doorman looks at my ID and sees I'm not from around here.
Correct. So step 2, authentication. The AMF creates a request. Hey, home network, is this person legit?
But it can't call home directly. It has to use the airlock.
Exactly. It hands the request to the VSEPP. The VSEPP encrypts it, fires it over the N32 to the HSEPP back in the U.S.
The HSEPP gets it, unwraps it, and gives it to the UDM and AUSF.
The AUSF runs its crypto check, UDM checks your account, and if it's all good, they send a success message all the way back to the SEPPs to London.
Okay, I'm in. The network knows I'm me, but I can't check my email yet. No IP address.
Not yet. Step 3, session setup. The AMF now tells the SMF, the traffic controller, to build the data path.
And the SMF has that big choice to make.
It's huge choice. It checks the PCF, the rulebook, and sees local breakout is allowed for you. So it decides not to route your data traffic home.
It picks a local exit door instead.
It picks a local UPF gateway right there in London.
So then what, step 4?
Step 4 is connection. The SMF tells the tower and the UPF to establish a tunnel. And just like that, you have a path. Phone-tower-London UPF-internet.
And boom, I have a 5G signal, I open my browser, and it works.
And the data flows directly out to the London internet, fast and low latency.
But what about my home network? Are they just out of the loop on the data side?
Oh no. Step 5 is reporting. The SMF in London is counting every single megabyte you use
For the bill.
for the bill. It periodically sends usage reports back through the SEPPs to your home network so they know what to charge you.
It's amazing when you lay it out like that. That entire cross-continental negotiation happens in, what, seconds?
Milliseconds.
Yeah.
A couple hundred milliseconds tops.
And we just take it for granted. You land, you get that welcome to the UK text, and it just works. But behind that simple experience is this massive automated dance.
It is a marvel of distributed computing happening for millions of travelers all at once.
So let's wrap this up. We started with a bowl of alphabet soup. I feel like we've sorted it into a nice, organized bento box now.
I hope so.
If you had to boil down the soul of this diagram, the one big takeaway, what would it be?
For me, it's the concept of logical separation. The architecture makes a very deliberate split. We keep the data local for physics reasons. Speed of light, latency, that's the bottom layer. But we keep the control, the identity, centralized for business and security reasons. That's the top layer.
Identity stays home, but the data stays local.
Precisely. And the SEPP is the guardian that makes that split possible and safe. It allows for a global network without exposing everyone's critical infrastructure.
That's the aha moment for me. It's not just a technical diagram. It's a security protocol for globalization.
It really is
Yeah.
how openness and security can actually coexist.
So here's a final thought to leave you with. We talked about how the SEP hides the network map from other operators, and it makes you think. In a world where cyber warfare and threats against critical infrastructure are very real, this architecture isn't just about loading your Instagram feed faster. It's a form of digital border control.
It absolutely is.
Every time you roam, your digital identity is passing through this incredibly heavily guarded checkpoint, this N102 interface that most of us never even knew was there.
It's the passport control that never sleeps. And it's checking your papers every single time you connect.
Thanks for joining us on this deep dive. Next time you see that little R on your phone's signal bar, you'll know the incredible dance that's happening behind the scenes. We'll see you on the next one.
See you then.